Theorem 19. Let's look at the first theorem that we'll have for a parallelogram. And it says that opposite sides of a parallelogram are equal and the opposite angles are equal. I think that's pretty self-explanatory, but here are the opposite sides. These two sides are going to be equal to each other. These opposite sides are going to be equal to each other. And also the opposite angles here are going to be equal to each other as well. So let's just dive right on in. We've already stated our given, and we're trying to prove what we just stated. Let's state the first obvious one. We're going to say that AD is parallel to BC, and that AB is parallel to DC. This is the definition of a parallelogram that we just covered. The opposite sides of a parallelogram are parallel. All right, perfect. Piece of cake. We could also say that number 3, we can say angle A equals angle C, and angle B equals angle D. Why in the world can we say that already? Well, we've learned previously that when the sides of an angle, of two angles, are parallel to each other, left to left and right to right, then those angles are equal. We have angle A here. This is the left side of angle A. Again, you have to be at the vertex of an angle and act like you're looking out of that angle. And so this would be the left side of this angle. Angle C, if we were standing here looking out towards the angle, this would be the left side of angle C. So left side to left side, they're parallel. We've stated already that these two lines are parallel to each other. So the left side of this angle and the left side of that angle are parallel. And the same thing would be said about their right side. Right side to right side, they're parallel. And we've learned that angles whose sides are parallel, right side to right side, left side to left side, then the angles are equal. So let's write that down. Angles whose sides are parallel, left to left and right to right, are equal. And that was a little bit ago, Theorem 9. All right, next one, we're going to draw an auxiliary line. Draw AC. So I'm going to just make a rough line here. Draw AC because, and I need to actually move this down one line. There we go. 2 points determine a straight line. We have point A with point C. We can combine them and make a straight line. 2 points determine a straight line. We can easily state something about AC, that it equals itself. AC equals CA. Identity. Just flying on through. I think by this point, some of these ideas are pretty basic. I'm going to label this angle up here and this angle down here. Angle 1 is technically angle DCA, and angle 2 is BAC. Alright, let's state that angle 1 equals angle 2. We have stated already that this is parallel to that. This would be technically a transversal, cutting these two parallel lines. That would make those two angles alternate interior angles. They are angles within, inside, or in between, I should say, the parallel lines, and they're on the opposite side of the transversal. So these are alternate interior angles, and we've learned that alternate interior angles of parallel lines are equal. Alternate interior angles of parallel lines are equal. Awesome. Now we have quite a bit that we've stated. We've already stated that obviously this line is equal to itself. We've stated, and let's get, this says equal to itself. We've stated that angle 1 equals angle 2. And we have also stated that angle B, this angle, is equal to angle D. All right. So we can state that these two triangles that was formed by this diagonal are congruent to each other. We could say triangle ABC is congruent to triangle CDA by SAA, side, angle, angle. There it is. We've learned that a bit ago as well. And then we can now say that AD equals CB and DC equals BA, because now that they're congruent triangles and then that means corresponding parts of those two triangles are equal to each other. And so CP, CTE, corresponding parts of congruent triangles are equal. A pretty simple and basic theorem there, and a pretty basic proof as well. Let's go right on into some of the corollaries for Theorem 19. Corollary 19.1 says that all sides of a rhombus are equal and all sides of a square are equal. And I did something interesting that may kind of make you scratch your head. I mean, we see two different kinds of quadrilaterals, two different kinds of parallelograms in this corollary, rhombus and square. But I go straight to saying square, because obviously a rhombus as a square, the squares are not rhombuses, but all rhombuses are, all squares are rhombuses. I think I totally messed that up. You can have a square, and if you have a square, you also have a rhombus. But if you just have a rhombus, you don't have a square. You have to have a right angle, obviously. But by definition, we've stated that a square is a rectangle, so it has one right angle, a rectangle with two adjacent sides equal. We've stated that a rhombus is a parallelogram with two adjacent sides equal, so they have a similarity. They're both quadrilaterals or parallelograms that have two adjacent sides equal. We're trying to prove, first of all, that this square is also a rhombus. We've got to prove that because that's part of our corollary. And we're also going to prove that all the sides are equal, that AB equals BC, which equals CD, which equals DA, that all the sides of this quadrilateral are equal. All right, let's get started. We can say in step number 2 that ABCD, we could say quadrilateral ABCD is, oh mamma mia, is a rectangle having two adjacent sides equal. And I'm going to just be very specific. I'm going to label which ones that I'm going to choose are. We can choose any adjacent sides, any two adjacent sides. I'm going to say that AB is equal to BC. That'll come in handy in the next couple steps or so. And we can say this statement because that is literally the definition of a square that we have. That a square is a rectangle that has two adjacent sides equal. There we go. So we're just stating the information that we know for sure. Number 3, we're going to state another thing, that this quadrilateral ABCD is a parallelogram, one of whose angles is a right angle. I hope we know what definition that is. That's the definition of a rectangle. So we're now trying to make it as basic as possible. We started with a square. We defined what a square is. It's a rectangle that has two adjacent sides. Well, now we're going to define rectangle. A rectangle is a parallelogram who has a right angle. And it doesn't matter which angle we choose. We just need to know that it has a right angle. All right. Well, really the main reason we may need that is to know that it's also a parallelogram, because the next thing we're going to say, number 4, is that ABCD is a rhombus. We have enough information to state that it's a rhombus, because the definition of a rhombus is that it's a parallelogram parallelogram that has two adjacent sides equal. So we've stated that we have a parallelogram here, that ABCD is a parallelogram, and we've stated that ABCD has two adjacent sides. So that means, by definition of a rhombus, that this quadrilateral is also a rhombus. Hallelujah. All right, number 5. We can now say that AB equals its opposite side, DC. We know that AB equals DC because we've stated now that it's a parallelogram, and we've learned that opposite sides of a parallelogram are equal. Let's also fit in the other opposite sides. AD equals BC, and that'll be our reason. We've learned that opposite sides of a parallelogram are equal. Perfect. And then now we can use our substitution axiom. We've already stated that two adjacent sides are equal, but AB is now stated that it's equal to DC. If AB equals BC, but AB also equals DC, then that means BC also equals DC. And we could do the same thing for over here, AD, BC. If BC equals AB and BC also equals AD, then AB equals AD. So every single side equals itself because of substitution. You can substitute these two for each other. So let's now say that AB equals BC, which equals CD, which equals DA. And that would be our substitution axiom. Corollary 19.2, it says a diagonal divides a parallelogram into two congruent triangles. So we're given a parallelogram, ABCD, with a diagonal. And we have diagonal BD. We're going to try to prove that this triangle is congruent to this triangle. Very simple proof. Let's do this very quickly. Since it's a parallelogram, we know that opposite sides are equal, so we can state that AD equals CB and AB equals CD. Again, opposite sides of a parallelogram are equal. Number 3, we can state that BD equals DB because of identity. And now we can say the two triangles are congruent. Triangle ABD is congruent to triangle CDB. Before I say the reason, let's just see all the stuff that I just said. Because opposite sides are equal in a parallelogram, this is equal to that. So I'm going to mark that. That is equal to that. The other opposite sides are equal to each other. And then we have this equal to itself. And I hope you can kind of see it here. This triangle is congruent to this triangle because of side, side, side. There are three sides equal respectively in two triangles, and so that would mean they are congruent to each other by side, side, side. Pretty simple one. If you need to look at that again, feel free to rewind. But let's move on to Corollary 19.3. Parallel lines included between parallel lines are equal. Just for those who may be a little confused here, this is not what it means when we say parallel lines are included inside parallel lines. All right, this is not it. It has the connotation that the lines that are included in between, they end between them. These lines could just keep on going forever. So that's not what we're talking about here. All right, so we have two parallel lines here. We have line AB and DC being parallel to each other. Some people like to use these kind of things showing parallel, that they're parallel. And then we have AD and BC here, and we've also stated that those are parallel because of this corollary. We have parallel lines included between parallel lines. And so I'm going to make 2 marks here showing that those are parallel. We're trying to prove that these 2 lines are equal to each other, that they have the same kind of length, I guess you could say, that their lengths are equal, so that AD equals BC. A pretty simple 3-step kind of proof. We've stated the given that we have 2 parallel lines and then 2 more parallel lines included between them, and that's all we're given. So now let's state number 2, that when you do that, you get a quadrilateral A, B, C, D. You can label it anything, and that quadrilateral that's been made is a parallelogram. So quadrilateral ABCD is a parallelogram because of the definition of parallelograms. Definition of parallelograms. We stated that the opposite sides are parallel. That's literally the definition of a parallelogram. The opposite sides are parallel. And that's literally all we've been given. So if this 4-sided polygon that was created when we put parallel lines in between the other 2 parallel lines, if that's now a parallelogram, that means that AD equals BC, because we have learned that opposite sides of a parallelogram are equal. Very simple idea for corollary 19.3. All right, corollary 19.4, and then we will be done. Corollary 19.4. It says that 2 parallel lines are the same distance apart everywhere. No matter which point we choose to pick on between 2 parallel lines, they will always be the same distance apart. There's our definition for distance. Remember we said the distance between 2 parallel lines is a point from one line perpendicular to the other parallel line. So that is very important to remember, because we're going to use that in our very second step. So let's see our given. We have AB parallel to CD with distances AC and BD. All right. And obviously they're between them. And we're trying to prove that AC equals BD, that they have the same distance between these parallel lines. Step number 2, we're going to use that definition of distance between parallel lines and make a statement. We're going to say that AC is perpendicular to CD, and we'd also know that BD, oh mamma mia, that was a very large eraser. BD is perpendicular to CD. And that's the definition we came up with, and we have definition of distance between parallel lines. Number 3, since these are perpendicular to the same exact line, this is perpendicular, and I might even just draw those markings there showing that they're right angles. Since they're perpendicular to the same line, we've also learned, I believe it was a postulate saying if 2 lines are perpendicular to the same straight line, then those 2 lines are parallel to each other. So we can say that AC is parallel to BD. And that would be lines perpendicular to the same straight line are parallel to each other. Step number 4, we can now say that AC equals BD because of the corollary we just talked about. Parallel lines included between parallel lines are equal. Parallel lines included between parallel lines are equal. And there we go, corollary 19.4. We got these 2 to be parallel to each other, and since these are now parallel, between parallel lines they have the same distance. They are equal to each other, and so since this is that, These are the distances between the parallel lines. We just proved corollary 19.4. Two parallel lines are the same distance apart everywhere.